We now show an example which is less appealing but more tangible, and with the advantage that it already shows a problem occurring in one dimension. And it's the following. It's a theorem, and it says the circle, we denote the circle by S1, so this really is just a subset of the plane, a one-dimensional set of the plane, so this is a one-dimensional set. The circle can be written as a disjoint union of events, countably many sets, E1, E2, E3, etc. And these sets, they are all rotations of E1. So E1 is a very funny set. We cannot really draw it because you see this is a very problematic set. So E1 is a set like this, and then E2 would be just a rotation of E1, E3 will be just a rotation of that, E4 will be just a rotation of that, which is basically the same as just a translation if we were to cut the circle here and open it. So this is really just a translation, except that it wraps around here. Before we discuss why the existence of this set causes us some serious problems from the point of view of measure theory, let's sketch the proof of this theorem. The proof would be, the sketch would be the following. Start with some very small set here, E1. Let's say E1 can be just a point here, and let's say an angle, another point here maybe, that let's just make this angle an irrational multiple of 2 pi. So 2 pi is the angle here. Now let us denote all the rational numbers between 0 and 1 by R1, R2, R3, etc. So let's just enumerate all rational numbers between 0 and 1 in a certain way. Let's fix it, and so that 0 will be the first one. And we'll do the following. Let this set here be our E1. And now consider E2 to be just E1 rotated by R2 times 2 pi. Then, since this was an irrational multiple of 2 pi and R2 is rational, we have E2 will be disjoint from E1. Now let's make E3 equals E1 rotated by R3 times 2 pi, and so on. When we do this, we get a family of sets which are disjoint. However, of course, their union is not the entire circle S1. Now what we can do from here is, let's change this E1, let's make it bigger, let's take a new E1, E1 prime here, to be E1 union some angle theta, and I'll choose theta so that it is not in any of these sets. And because of these sets, they contain all possible rational rotations of the original set, when I consider this E1 prime here, and through the same process we define E2 prime, E3 prime, etc., we have again a collection of sets. These are larger sets now because we have added a point to each of them, but they're still disjoint. They're still disjoint. They're larger, and they're not yet big enough so that their union gives the entire circle. So we can keep doing this. Increase these sets once more, and then once more, and then once more, and keep doing this. But we not just keep doing it. Now we are using some very complicated property of induction, which is not really induction because it is uncountable in the end of the day, but it is possible to increase these sets indefinitely, or not really indefinitely, until the point when we get really some E1, let's call it tilde, such that when we define the other ones and keep going, they are still disjoint. This property is never violated, they're still disjoint, but now they became finally big enough so that their union is the entire circle. So this is a sketch of the proof, and it's a sketch exactly because we are not explaining properly this process of making it larger and larger until in some very far away future we get a set that can no longer be increased. Now, what have we learned from this theorem, or what is one first consequence of this theorem? The consequence will be the following. If we suppose that the first set of this disjoint union that builds back the circle, suppose it has a length. Suppose it can be measured and it has a length, let's call that length L. Then all the other sets, they're just rotations of this one, so they will have the same length, which will also be L. If this length L is 0, then by sigma additivity, the length of the circle is 0. And we know that's not true. The length of the circle is not 0, it is 2 pi. On the other hand, if L is positive, then by sigma additivity, the length of the circle will be infinite. And we know it's not infinite either. So what can we conclude? Well, the assumption was incorrect. We cannot really assign a length to this set E1. So these sets, they are not measurable. We cannot measure them and assign a length to them in a proper way. So this example, as well as the previous one, the Banach-Tarski paradox, what do they show? They show to us that if we want a measure that will satisfy these three properties that are non-negotiable, we really want these three properties to hold, then necessarily we'll have sets which are not measurable. And this is called the measure problem. So what is the response that we have for the measure problem? Well, this is the question. What is the solution that we have to this problem? And the answer is the following. Modern measure theory, what it does, it will work with measures that satisfy all those three properties we want them to satisfy, but they are not defined on every subset of our sample space. Instead, they are defined on a class of sets which is large enough to be useful, and you see it's extremely useful. We'll rarely fall into any questions where lack of measurability of some specific set poses any trouble, and it is small enough so that those properties will hold. And finally, this is the reason why all this formalism of talking about a sigma algebra in a probability space or a measure space, why it is necessary, and this is why we have to talk about the sigma algebra instead of just work with the set of all subsets of the sample space. Or, well, not really. Let me just briefly mention that later on we'll see that sigma algebras are actually much more useful than just a way to circumvent the measure problem. And sigma algebras, they encode information. They are a fundamental object when we study martingales, independence, conditional expectations, etc. But let's leave this aside for now.